Okay, this section I'm just going to show you the notation for higher order derivatives, which you might use later on in your calculus course. The first derivative of a function can be represented as y prime f prime of x dy over dx or df of x over dx. This notation is generally reserved for differential equations. The second derivative, you use y double prime f double prime d squared y over dx squared or d squared f of x over dx squared, and then capital D squared with respect to x of your function for differential equations. And then for third derivative, y double prime or f triple prime, and then here you just change these numbers to 3 for the third derivative, and then over here change this number to 3 for the third derivative. Now if you want anything higher like fourth, fifth, or sixth derivative, you would just write in the number here. So if you wanted the fifth derivative, you would do y and then put, for n, you would put 5, or on any of these you would just put 5 in for the fifth derivative if you wanted to go higher than that. Now when you get into sequences and series, you'll actually see why you need third, fourth, fifth derivatives and so forth. But in here we're only going to focus on the first and second derivatives for the most part. Now let's talk about velocity and acceleration. Suppose you're sitting in a car driving down the highway. There's a relationship between the position of your car and the time you travel. So in other words, your position changes as time changes. Suppose we had a function that represented this relationship. We will call this function s of t. So that function is actually going to be, there it is, that function is going to be s of t. Now, where s is the distance and t is time. In our case, s is in miles and t is in hours. What represents the rate that your position changes with respect to time? I bet you can answer that. It's velocity. So if you're traveling 30 miles per hour, then your position is changing at a rate of 30 miles per every 1 hour. If you're traveling at 100 miles per hour, your position is changing at a rate of 100 miles per hour, and dangerously unless you're a NASCAR driver. Now that we have established that velocity is the rate that position changes with respect to time, how would we get this velocity function from our position function? Aha! The derivative represents the rate of change. So velocity can be found by taking the derivative of the position function. So let's say your position function is s of t equals 4t cubed plus 20t plus 10. Then your velocity would be the derivative of that, which would be 12t squared plus 20. And so if t is 2, your velocity would be, just plug 2 in, you get 12 times 4 plus 20 equals 68 miles per hour. Okay, let's move on. Now suppose you step on the gas in order to pass a vehicle. Guess what's happening now? Your velocity is now changing with respect to time because you're speeding up. Speeding up is acceleration, slowing down is deceleration or negative acceleration. Acceleration is simply a change in the velocity with respect to time. So if we wanted to find acceleration, we would need the derivative of the velocity function, and the velocity is a derivative of the position function. Put it all together and it means that acceleration is the second derivative of your position function or the first derivative of velocity. So go back to my function. We know that the first derivative up here is 12t squared plus 20. So the second derivative of the position function, s double prime, would be the derivative of that function, which is 24t. So that's what acceleration is. Acceleration is the second derivative of your position function or the first derivative of your velocity function. So if we wanted to know the acceleration when t is 2, then you would plug t into this function and you would get 24 times 2, which is 48 miles per hour or per hour squared. So again, position is s of t, velocity is s prime of t, and acceleration is s double prime of t, the second derivative. Okay, we'll end this with a simple example. Since the moon has no atmosphere, a falling object experiences no air resistance. In 1971, an astronaut demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for these objects was actually s of t equals negative 0.81 t squared plus 2, where t is the time in seconds and s of t is the height in meters. Find the ratio of the Earth's gravitational force to the moon's. Okay, so basically what I need first is I need to find the acceleration. So the acceleration here, remember, acceleration function is actually the second derivative of position. So to get to that, let's find the first derivative of position. So the first derivative using the power rule would give me negative 1.62 t. And then the second derivative of that would just give me the constant negative 1.62, and that would be in meters per second squared. Now the Earth's gravitational force is actually 9.8 meters per second squared. So to get the answer just of the ratio, just take negative 9.8, divide it by negative 1.62, and you'll get that the ratio is 6. So you can see that that number is 6, and you've probably heard that number before about gravity being 6 times stronger on Earth than it is on the moon. So there you have it. And that's really all I have for this little short section. So we'll go ahead and move on to the chain rule in the next section.